Mhm. Cool, can you hear me? But as someone who's spent a lot of Hubble time observing TRAPPIST-1, I hope we still care about it for at least a year or so until I finish the paper. Yeah, so I'm not going to talk about TRAPPIST-1. I'm Dave Wilson. I'm from the University of Colorado. And I'm going to talk about some of the ways that we measure interstellar winds, and particularly concentrating on the technique that I've been working on using white dwarf binaries to measure the winds. So why do we care about stellar winds? It's really nice being at cool stars and not an exoplanet conference where I can actually say I care about the star for the star's own sake. Don't have to worry about little specks orbiting them. But we do care. They do matter for exoplanets of stellar evolution. We want to know like what the star is doing in its upper atmosphere and also the effects it's having on other planets. But it's really hard to measure. The way you measure the solar wind, of course, is you measure it in situ. You put a spacecraft out to the between us and the sun, and essentially stick its finger out into the wind and measure the wind rate and density. We can't do that for stars. So how can we measure these extremely faint signals remotely? And until this morning, I would have considered these to be the main techniques to go for it. Apparently, we can also do it with radio. That's cool. But I'm going to look on this. So we've heard a lot about the atmosphere, so I'll kind of go through that quickly, but then talk about doing it with white dwarfs. So for astrosphere detections, this is my extremely detailed and very artfully done artist impression, where we see the interaction just with the sun. We see the interaction with the ISM and the astrosphere, and this creates a dense hydrogen wall at the astropores, where in Lyman alpha observations. So here showing, we've seen already, Lyman alpha observation, where the line at the top is what the intrinsic emission from the star looks like. That intrinsic emission is brought down to the observed spectrum by absorption from the ISM, and we see extra ISM absorption from the astrosphere if we're lucky. This has pros. It gives us a wind at single stars, which the white dwarf technique does not, and covers a range of spectral types. And it's kind of free. We want to look at the Lyman alpha lines of stars for many different reasons. So these observations come with that. The cons is you need high-res UV data. You need the Stissa shell modes, which puts a real limit on sensitivity. Depends on the viewing geometry. You have to get lucky, so you see the astrosphere absorption. And because of the way the ISM is ionized in different places, this only really works out to about 7 parsecs. So there's a hard limit, both observationally and physically, on how many stars that this will work for. So instead, we can use white dwarfs. So these are this is a animation I made. This is completely to scale. So the size of the two objects is to scale, and the separation, and the orbital period sped up by about 10,000. This is CC SETI, I think, without orbital period. But there are many of these stars. So you have an Earth-sized white dwarf and an M star, or many different types of spectral type, mostly M stars, because stars are mostly M stars. The white dwarf is sitting in the stellar wind of the companion and will accrete it. And so you have a spectrum that looks like this. This is my favorite spectrum, where we have most of the spectrum here is a white dwarf. It dominates. This is an ultraviolet spectrum, so the high temperature white dwarf dominates. But in that white dwarf spectrum, we have emission from the M dwarf poking through, but also these absorption lines. And because the white dwarf has an otherwise pure hydrogen atmosphere, we know that all of that absorption from different metal lines must be coming from the wind. The white dwarf is accreting the wind, and through techniques developed mainly for looking at planetary accretion, we can back out the accretion rate onto that white dwarf, and thus by assuming making a lot of assumptions about the geometry of the system and how the white dwarf accretes that wind, we can turn that accretion rate onto the white dwarf into the mass loss rate from the M star. Again, these are pros and cons. The main one is there are thousands of them. So we could do this a lot, and we could do this over a whole range of spectral types. As I said, it's mainly been white dwarf M dwarf binaries, but research now is pushing up into looking at white dwarfs with earlier type stars around them. And they're relatively simple observations. You can occasionally do this in the optical. There are absorption lines there. Ideally, you still want UV, but you don't need the high-res, often multi-orbits Stisser shell observations. You can do this with a single COS spectrum, one visit with Hubble. The cons, though, you still need the UV ideally, and these might not be representatives of single stars because they are tightly locked to those orbital periods. And you saw those orbital periods are hours. These M dwarfs have been spun up, so their activity and thus their winds might not be representative of single stars. And also the conversion from accretion rate to wind rate is tricky and has a lot of assumptions, but as does all the other techniques. But this is where kind of we're at. So this is looking at all of the wind measurements I could find up until a few weeks ago. And we got a good spread out to about 1.2 stellar masses. So in single stars, this is mainly astrosphere measurements and a few other techniques. And then previously published binary stars in orange, and then my sample I'm studying in blue. And I've put on the sun there just for comparison across the whole plot. And you can see it's kind of a mess. There doesn't seem to be a trend with mass. There's a lot of scatter. It does look like they trend downwards at lower masses, but only a little bit. So we really might not be able to get a good relationship between stellar mass and wind rate. There is some hope with X-rays. We've seen a version of this plot before. So this is the comparing wind rate as a function of surface area of the star with X-ray flux, and there is a relationship there, but again, there's a lot of scatter around it, and scatters by orders of magnitude, so you can't go directly from X-ray flux to wind rate yet. And I've put some of the stars to the binaries which I have X-ray measurements on there, and they don't seem to follow the trend either. So maybe we can do this with X-rays, but maybe not, and there's still a lot of scatter there. So conclusions, it's worth pointing, measuring stellar winds is hard, and it's worth pointing out that we cannot yet, maybe ever, just point at a star and say, what is the stellar wind of that star? All the techniques have to be used ensemble and get enough observations of as many different kinds of stars so that when we want to look at a star of interest, know what its wind is, we have enough measurements so we can pull from to infer the wind of that star. We're very unlikely to be able to point at a star and say, what is its wind? Astrosphere detections and all the detections of single stars are great, but limited number. White dwarf binaries offer a huge number of targets, an increasing number of observations of them, but they might not be representative of single stars. That is it. Oh, that's the sun. Sorry. Yeah, I extended the sun across the whole plot just to show the comparison. Sorry. Yeah. Sorry. Oh, yeah. Sorry. The question was, what is the straight line? Yeah, it's the sun. Yeah. Yeah. No. Yeah. Well, I guess what'd be nice is to see a trend with something. So yeah. So a point in the end was like we can't do this at any given star. So that if there isn't a trend of any, and yes, it's a good idea to do this with X-ray flux or rotation. Rotation is where you're going to be really killed by the binaries because they're spinning so quickly. But yeah, if there isn't a trend of anything, we're kind of screwed. So hopefully we'll find one.
hear me?